-2 coulombs and 12 coulombs. Those are my surfaces. And right now I'm finding the electric field at that point right there. How do I handle it?
Logically, I would say it's just 0.
It's not 0.
That's a shame. That would make my life easier.
Some of them will be 0, but that one's not. We got to exploit the spherical symmetry.
Can we use the equation for the electric field, the constant and everything, and then treat it as like radius or something, or multiply by?
If I've got spherical symmetry, and I'm outside the charge, the spherical symmetry, I treat it like a point charge. If I have a spherically charged surface and I'm inside, what is the electric field from that?
Inside 0.
Say it again?
Inside, it would be 0.
It would be, yes. So the only thing I need to worry about is what is inside the surface. We can use Gauss's law, or I could just use the shortcut we've already done. These all have spherical symmetry. I'm inside all of those. I can ignore them. That's the only one I need to worry about. So it's going to be Coulomb's constant times 5 coulombs divided by the distance, 0.01 meters.
1.12 times 10 to the 25.
Say it again?
1.12 times 10 to the 25.
No, I'm not buying 10 to
5
25.
times, hold on. 5 coulombs is 5 times 10 to the 9th, right?
So this is 9 times 10 to the 9th times 5.
Oh,
Should be
just
divided by
10
0.01.
times 10 to the
Oh, sorry, 0.01 squared. It's not by 25, but
that was just.
45 times 10 to the
either 6.
13th, or 4.5 times 10 to the 14th.
I got 12.
10 to the 12. I went too far. Okay. You use 8.99?
Yeah.
4.495 times 10 to the 12 units,
Would it be,
Newton meters.
coulombs?
not Newton meters, what'd you say? Yeah, newtons per coulomb. Newton meter is joule.
I was thinking of meters per meter, but that's still.
Yeah.
I'm getting to the 14th.
You are getting to the 14th. All right, so it was, that's to the 9th, 10th, yeah, 14th makes more sense.
Did you square 0.01?
Oh, you didn't square the.
Oh, I didn't square it?
Yeah, I added that in after the fact. Is it 14?
Yeah.
Yeah.
5 coulomb charge is huge, so.
Wait, 0.1 meter, 0.01 meter.
Wait, oh, it's, wait, I said 1 centimeter away.
It's 2 centimeters though.
No, you said that was 1.
I'm finding the electric field at 1 centimeter. The cavity here is 2 centimeters big,
So the radius.
but I'm just finding the electric field halfway in between.
Yeah, but you put 2 centimeters down there.
Yeah, that's the distance from the 5 coulomb charge to that inner surface.
That's not.
I'm
defined.
asking for the electric field when I am here.
Oh, halfway in between it?
Yes,
Oh, okay.
that, the scribble right here is 1 centimeter.
And why?
Yeah,
Is
why?
that- Why are you
Why are you
looking for
looking
the field there? Halfway between the point and the
Why not?
edge?
I
Oh, you just
I
picked it
wanted to.
randomly? Oh, okay.
Well, I mean, I could have picked any distance, I wanted specifically that point that was halfway in between. John and Scars.
Is it like an equilibrium point or something between the charge on the inner surface and the charge in the middle, or?
No, the charge on the inner, because I'm inside that inner surface, I don't care what that is.
Oh, it doesn't matter where it is on the inside?
If I've got spherical symmetry, it doesn't, as long as I'm inside that, it doesn't. All of that's irrelevant for the first problem. I go to 4 centimeters, so that's gonna be somewhere around here. What's my electric field?
It should just be,
Do you also know, account for the one beside it?
you'd have to account for the
I,
five.
because it's all spherically symmetric, anything outside that, I don't care about.
It'll just
Oh,
be-
so it'd just be -5 instead of 5?
No,
So,
you'd have to add them.
so what's the electric field?
It would be K constant 5 coulomb over 0.04 meters squared plus K constant -5 coulomb over 0.02. No.
If I'm outside spherical symmetry, I treat it like a point particle.
This is,
You're I mean, you can do it, the approach that you're taking right there, as long as you recognize that inner surface here, I treat it like a point particle because I'm outside that, but and I didn't mean to erase it, but I erased the key point over there. That would have saved you any math. Yes, Ryan, say it loud.
Isn't it just 0?
It's 0. It's an electrostatic equilibrium. I'm inside the conducting inside the conductor, not at a surface. The electric field is 0. Excess charges are settled on the surface, and rewrite what I had over there. Electric field inside conductor. In other words, not at surface. Is 0.
was the first one was at the surface? Why was that not
The
there?
first one
first
was
one
not
was
on the
at the-
surface, it was in the hollow area.
Yeah, the first one we did was up here.
Can you explain electrostatic equilibrium again really quick? Because you say that each surface or each shell has like a total charge, but then the static equilibrium means that they should be at 0.
Electrostatic equilibrium, the charges, imagine to start out with a sphere, put the excess charges on it, and they spread out. So initially, it's not an equilibrium, the charges are moving all over the place. When they finally settle down, which if I took a metal sphere like this and added excess charge, we're talking microseconds, that doesn't take long. So once the charges have basically settled where they're going to fit, I mean, there might be some vibrations going on, it's not like we're saying that they're perfectly still, but we treat it as such. So these particles are now basically where they're gonna be. That's electrostatic equilibrium.
Okay. So it'll still have a charge overall, but
Yes.
but just be stable or whatever in their current position.
Yes.
And where does the 0 come in then?
That if I have a conducting surface or a conducting object in electrostatic equilibrium, the charges will reside on the surface, and when they finally reach that equilibrium point, the electric field that's not at the surface, that's inside the conductor but not at the surface, electric field is 0.
Oh,
Because if the electric field is not 0, that means if I have an excess charge there, well, if the electric field is not 0, that charge is not gonna get moved.
okay.
So the further that we go down to do the same, like, basically it's a plug and chug, right? The further we go down, do we just add every single charge to it, or would it be different? Yeah.
Because once I'm outside that particular surface, then I just add up everything that's inside.
Okay, so once we're at 20 centimeters, we would have to add 5 coulombs, -5 coulombs, -3 coulombs, 10 to -2, 12? Or would-
No, you went too far there. So you do 5, negative, if you're doing that, 5, -5, 2, -2, 12.
Oh, so only the surface is not what's inside?
Well, this -3 is not inside. This -3 is indicating the total charge on this object,
Okay, so,
which would be the -5 and 2.
so that wouldn't count the further we go down. So like, if we're gonna get 12 centimeters, 20 there.
Yeah.
Oh, okay, yeah, if we're gonna get 20 centimeters, we would have to disregard the charge inside.
Yeah, so it would be the charge inside that 20 centimeters,
Okay,
that 20 centimeter radius.
okay.
So it would be 5, -3, 10.
Oh, so we take.
Or -5, or 5, -5 to -2, 12.
Oh,
The sum should be the same.
oh, okay. Oh, yeah,
If the sums are not the same, we've made a mistake somewhere.
okay.
All right, so at 4 centimeters, I'm inside the conductor. I'm not at a surface. The electric field should be 0. I guess that really at 7 centimeters, I am now in between the 5 and 8. I am here. What's my total charge inside?
5 coulomb plus the -5 coulomb plus the 2 coulomb.
Yep. Yeah, 2 coulombs. So this is gonna be Kc times 2 coulombs over 0.07 meters squared. Which is some number smaller than that.
3.67 times 10 to the 12.
Did you square?
Yeah,
I don't think you did.
really?
It should be smaller than that. Oh, it times 10 to the 12 is.
This,
I'm sorry about that. Is it?
Yeah,
Is it
same.
12?
yeah.
All right, at 10 centimeters, I am now around here. What's the electric field at that point? Yes? Right, way complicated there.
Would it be 0 again?
It would be 0 again.
We're inside the conducting material.
Absolutely. And then at 20 centimeters, I'm now outside of the whole thing. It's got spherical, spherical symmetry. You can treat it like it's all a point charge. And so it becomes that electric coulombs constant times my total charge of 12 coulombs over where I am, place 2 squared.
2.7 times 10 to the 12.
So wherever the point is, anything inside of it is treated as a point charge.
If you have spherical symmetry.
And you would say, let's say in the problem, there's symmetry. or-
Yeah. Or if I said it's a sphere in electrostatic equilibrium, then. Or, yeah, so it's either that or I state explicitly it's got spherical symmetry. Or uniform charge density. If it's an insulator and said uniform charge density, then we're doing the same type of thing.
So for the 7 point in there, it's 5 plus the -5.
Plus the 2.
Oh, because you're taking both of them because, wait, why can't you just take the -3?
I could do the
Oh,
5 and the negative.
5 and the -3, okay. Because you're only worrying about the total charge of everything.
Yes.
Okay.
The other time you can make a point charge approximation is if you are far enough away.
And then outside of it at the 20, it's 5, -3, and 10.
Yes.
Okay.
So if I gave you a non-symmetric symmetry on an object that was, you know, about that big, and I went a mile away, that's close enough to a point charge.
Probably close enough to 0 too.
Yeah, that too.
Huh?
Could you do this with like a, instead of a sphere, like a cube or something?
I feel like that gets more complicated.
Yeah, or it can be done. Can I do a cube cold if I'm just out? So if I had a cube.
Like a cube inside of a cube or something?
You could do. You could do the electric field, so if I had a cube inside it, so let's say that's a 5 coulomb charge there, and then I've got an excess of, we'll just say -3 coulombs, we'll keep the same numbers. Then, I know that the same type of reasoning as before, I'm gonna have -5 coulombs on this inner surface here, and 2 coulombs on this outer surface. Same reasoning as before. The electric field inside here is still 0, assuming that that's all conductor. If I ask you what is the electric field at that point right there, that becomes incredibly difficult. And I'd have to pull out my, in essence,
I
pull
thought the
out
whole
Jackson, and probably, it would take me a while to remember how to do something like that.
Weren't they saying that, with the electric field, it doesn't matter the type of surface though, because it's all putting out the same electric field, so if you have somewhere outside of it, then it's being influenced the same?
No.
No?
No, if I have the spherical symmetry, yes, but I don't have spherical symmetry here. I'm gonna have charges, I'll have excess charges congregated here,
So,
some spread out over there.
so if it's a weird object, it's going to be putting out different electric fields all over it,
Yeah.
basically?
Yeah.
It's because some points are now further away from others.
Yeah.
So if I gave you something like that, I would ask you, the simple question of what's the electric field inside, what's the distribution of charge, or what's the charge on the surfaces? That stuff's easy to do. Or if I gave you something like this, and then I went far away. Not so far that it's 0, but far enough away that it's good enough to count as a point charge.
So practically, do they just try to make things spherical then, so they don't have to worry about complicated electrical fields, or?
And 252, yes.
Well, no, I mean,
And
in
actually-
real life, like when they design things, like, or is it just they have computers do the calculations, like for complicated objects?
They probably use computers, but for the most part, there is a lot of symmetry involved. I was trying to think in the superconducting super collider, I mean, it's a giant ring, and within that ring, you will have parts with constant electric field or constant magnetic field, created by things that are potentially circular or donut shaped. So, yeah, for the most part, I think it's rather inefficient. It's a rather efficient shape. One of the reasons manhole covers are round. It's a good job.
Donut shapes are efficient too.
They can be, depends on what you're doing.
I don't,
I was about to look at my watch to see what time it was. What time is it?
Basically, it means that we don't have much time left in the class because you're now.
Okay, that's the,
That's your
That's a- that's a
indicator.
cue.
I don't even need to remind you.
I was about to say, he now has an alibi because he walked in front of the camera, but he doesn't have an alibi for the rest of the class. All right. So as things start settling on, as we get into electrostatic equilibrium, things start settling. Excess charges settle on the surface, electric field inside the conductor is 0. But charges also if I had a square shape here, if I have a distribution of charge that's evenly distributed around, have I done this bit? Okay, at the point where I'm going, all right, did I do this with 152 or did I do this with 252 or both?
I think only 152.
You did not do this? Okay. If I distribute the charges evenly around the surface like this, I have forces still going on. If I look at the forces acting on this particle right there, it's getting pushed on by that charge, getting pushed on by that charge, getting pushed on by that charge, getting pushed on by that charge. I have more charges over here than I have over here. So in essence, this particle here is going to start to push towards this corner. And that's going to be true is that whenever I have these internal corners like that, more charges are going to get pushed towards it, and they'll get pushed towards it until I've got so many in that corner that they basically reach equilibrium. So excess charge will settle on the surface, yes. But also, the greater the interior angle, sorry, wrong one. The smaller the interior angle, the greater the concentration, the greater charge density. So if I spread the charges evenly throughout, that would not be electrostatic equilibrium, and they would start to spread out until I've got an abundance of charge here in the corners with fewer charges on the inside like that. If I then stuck a cavity inside there, so now and put a positive charge in the middle, I will have some charges come towards the inside here, but they will be concentrated here on the sides, with some on the corners. Because the interior angle is this, which is 270 degrees. It's a much greater angle, so I'm going to have much less density there.
You have 5 minutes.
Okay. So as these charges start aligning around the edge, we do have one thing that will be common no matter what the shape is. This might be going to what Phil was asking about earlier. The thing that isn't common is that the electric field at the surface will be perpendicular to the surface.